All right, so first of all, we have the test. You can take it Monday night. How many times have I written this stuff up here? Who wants to bet that somebody comes up to me the day of the test like, where's the test? Or on Friday like, can I still take the test? I didn't know that it is going to happen. Would not be a good bet. Okay, 13/26, and then Thursday, the 14th at 2 p.m. and 13/28. Okay, so I'm going to do an example of using the angular version of Newton's second law. So the equation we're going to use is this. You add up all the moments around the axis. It's equal to the mass moment of inertia times the angular acceleration. So let's say that we have, let's think of this, no, let's do it like this. Here's the wall. And there's a hinge here and a rectangular shape like this with a thickness of 10 centimeters, so 0.10 meters. And a length of 2 meters. And say the mass of this rectangle is 10 kilograms. And someone applies a 50 Newton force here. And we want to know what's the angular acceleration of the object. So first, I'm going to draw a free body diagram. So what are the forces acting on this? There's weight that acts at the center. And that's 10 kilograms times 9.81, so 98.1 newtons down. And then we have 50 newtons acting here. And then over here is the axis, the hinge that it rotates about. That's our axis A. And there's an unknown force vector that's applied to the body by that hinge. You know that since that thing isn't allowed to move, that the hinge has to apply forces to it to hold it in place. We don't know what those are. We could just write it like, I'm going to put it in a funny color because it turns out the forces that act at the axis, you can just leave out of the problem. They never show up in the rotational version of Newton's second law. But I'll write this as Fx and Fy. And then we have to calculate the mass moment of inertia. I gave you 3 ways to calculate the mass moment of inertia for a rectangle. One where it's right at the center, one where it's all the way at one end but in the center on the other side, and one where it's at the corner. This one is at the end, lengthwise, but at the center height-wise. Okay. So the formula we're going to use for this is 1/3 times the mass times, now the dimension where it's at the end is attached to the 1/3, so this is going to be 2 squared. And then 1/12 times 10 times the other dimension, the dimension where it's in the middle, squared. Can you see what I'm talking about? Like, it's at the end of this dimension, so that one is attached to the 3rd. It's at the center of this dimension, so this dimension is attached to the 12th. What? Oh, it should be a 12th. Sorry about that. Well, I'll give you the formula on the test anyways, but yes, there should only be thirds and 12ths. Okay, so this first term is 40 thirds, so that's 13 1/3. The second one is 10 12ths, 5/6, times 0.1 squared, which is 0.01. So that's a tiny, I think that's plus 0.0083 repeating. This is like 13.3 repeating. And so this is equal to basically 13.34. The units are, you're taking a mass for this formula and multiplying it by a length squared, so it's always kilogram meters squared. And now we have to think about the moments that these forces produce. Okay, so the force vector F, what moment do those forces produce around this axis? Well, they're acting at the axis. And remember that to calculate the moment, you have to have a distance from where the force is applied to the axis. So any force that acts at the axis doesn't produce a moment. Okay? It's like trying to turn a bull with a wrench by pushing down directly on the above the bull. It's not going to ever turn it. So this is 0. And then the weight force, if you draw the line from the axis to where that force is applied, those two are already perpendicular. So we can just calculate this moment as the force, 98.1, times this distance. What's that distance of that green dotted line? Yep. And then we have to think about the direction. If you applied this force and it was the only force applied, would it make it rotate clockwise or counterclockwise? It would make it clockwise, yep. If you applied this 98.1 newtons force there, and the axis is here, this force would make it rotate this way. So it's negative. That's because it's clockwise. So negative 98.1, and the units are newtons times meters. And then we have to do the same thing with that 50 Newton force. If this is applied at the corner, then notice that the line from where the force is applied to the axis isn't quite perpendicular to the force. You see that? if I draw this line, it goes from the corner up to, I mean, it's almost perpendicular, but not quite. But you can move this force along the line of action, along its line of action until it's perpendicular. So just imagine this force acting here instead. And then a line between where the force is applied and the axis is perpendicular to the force. And so the moment is 50 times what's the distance from this little blue dot to the axis? 2, yep. And would that force make it rotate clockwise or counterclockwise around A? Counterclockwise, so this one's positive. And so you get positive 100. And now that we've calculated the moments produced by all of those forces, we can put it into this equation. I haven't used that abbreviation before. This is, so put it into that sort of angular form of Newton's second law. So we have 0 minus 98.1 plus 100 is equal to 34, no, what was it, 33.34? 13.34 times alpha. And so positive 1.9 is equal to 13.34 alpha. So what do you get for alpha? .142, and that's radians per second squared. So is that angular acceleration clockwise or counterclockwise? Counterclockwise. So that means that even though this force is almost twice as big as this one, the combined effect of these two is to make this thing start to rotate counterclockwise. And the reason for that is this force is acting a lot farther from the axis than this one is. And so it has more of an advantage in producing the moment. Any questions about that one? Okay, so this one, let's think of this as like a seesaw. Let's say the axis is right in the middle. The length of the whole thing is 5 meters. And let's say there's a force of 500 newtons acting half a meter from the axis on this side. And a force of 100 newtons at the end on the other side. And the idea is this is connected to the ground. You know, this is like a hinge. So we want to see how this seesaw is going to rotate. we have to give a mass here. Let's say the mass is 30 kilograms. Oh, and that's 5 meters. I need a length here too. Let's say this is 0.2 meters. Okay, so draw a free body diagram. So what forces are acting on this board? There's the 100 Newton force here. There's the weight acting right in the middle. That's 294.3 newtons. There's the unknown force coming from the axis. I'm just going to leave that off, though. I mean, it is a force, but it's not going to produce any moment, so it doesn't matter to us in this problem. Oh, I'll put it on here as like, remember it's there, but it's not going to affect the problem. Okay. No, not for these rotational problems. And then 500 newtons here. So mass moment of inertia. The axis in this case is at the center of that rectangle, so we're just going to use 1/12 times the mass times 5 squared plus 0.2 squared. Can someone calculate that? Oh, 62.6? Okay. And the units are kilogram meter squared. Thank you. And now we'll calculate the moments. So the 100 Newton force. That one's really acting up in the corner. But we can just slide it down until the line between the axis and where the force is applied is perpendicular to the force. Remember what I'm talking about with that? And so the force is 100 newtons. The moment arm is 2.5. So you get 250 Newton meters, and we have to think about the direction. Would that 100 Newton force make it rotate clockwise or counterclockwise around the axis? Counter, yep. And then the weight. That's acting right at the axis. So we have 294.3 times 0. So that's not going to make it rotate. And then the 500 Newton force. Again, the line between the axis and where the force is applied isn't perpendicular to the force. But if we slide the force along its line of action to here, then it is. So what's the... Okay, so we have a force of 500. What's the distance from the axis to that new place where it's applied? 0.5. And would that 500 Newton force make it rotate clockwise or counterclockwise around that axis? Clockwise. So you get negative 250. Ooh, that just, I didn't even think about that, but it ended up coming out exactly the same. Okay, so now we can go to the angular Newton's second law. We'll add up all these moments. So we have 250 plus 0 minus 250 is equal to 62.6 times alpha. And that says 0 is equal to 62.6 alpha. So the angular acceleration is 0. Those two exactly balance each other. And you know that effect from seesaws, like if a smaller kid sits really far from the axis and an adult sits close to the axis, you can make it balance even though those weights are drastically different. Any questions about that? Yes? Okay. Well, I think really the easiest way to do that is, so imagine that this thing is free to rotate around this point, because that's the axis. Then just imagine what would happen if you pushed on it in that direction. Would it make it rotate this way around the axis or this way around the axis? Okay. And so that's, just like if this is free to rotate and the axis is my fingers here, okay, and I push a force there, would it make it rotate like this or like this? Yep. And so that's the way to do that. Yes? The whole thing is 5 meters long, so from the middle to the end is 2.5. Did someone else have a question? Yes. Which, say it again. These two? That's right. So there's 2 times that a force doesn't produce a moment. One is when the force acts at the axis, and the other one is when its line of action goes through the axis. Because then the rules say that you can move the force along its line of action. So you can just move it right to the axis, and it doesn't do anything. You want to see another problem like that? Okay, so let's say the length is 2 meters. The height's 1 meter. The mass is 5 kilograms. Let's say the axis is at the center again. And we'll apply a force to it like this. Let's say this time it's a top-down view. So let's say this force is 200 newtons. What's the angular acceleration? Okay, so free body diagram. We have the force over here of 200. And we have the force here at the axis that we can ignore. It's not going to produce a moment. Since it's a top-down view, the weight is acting into the page, so that's not going to show up in this calculation. The mass moment of inertia is 1/12 times 5 times 2 squared plus 1 squared. So that's 25/12. So 2 and 1/12. .083. Okay, so the only thing that could produce a moment here is this 200 Newton force. But notice that if you draw a line from the axis, so this is the axis here, right? If you draw a line from the axis to where the force is applied, it's not perpendicular to the force. So that's not going to work. So where are we going to have to move that force to along its line of action so that those will be perpendicular? Here's the line of action. Where do we have to move that to so a line from the force to the axis will be perpendicular to the force? Yep, middle. So we'll move it to here. Then we have the force going this way. We'll stop thinking that it's over there and think that it's in the middle. And now the line from the force to the axis is this. It's perpendicular to the force, so now that works. And now you might have thought that the distance we were going to use was this one or something, or this diagonal distance. But it turns out the distance that we're going to use for the moment is just this small distance, half a meter. Yep. So why can't you move it from that corner? So this dotted line is the line of action. And you can move a force anywhere you want along its line of action. It doesn't even have to be touching the body. You could, if it helped you do the problem, you could move this force out to here. Okay? And it doesn't change anything about the problem. It's just a tool for doing the calculation. Okay, so the moment is 200. So 200 newtons times the distance, the length of that green line, which is 0.5. And now if this thing was free to rotate around A, and you applied this force here, would it rotate clockwise or counterclockwise? Counterclockwise. So this is positive. So we get positive 100 Newton meters. And so the angular Newton's second law says 100 is equal to 2.083 repeating times alpha. So alpha is equal to, can someone divide 100 by 2.083 repeating? 48 0.007 radians per second squared. So which way is the angular acceleration? Counterclockwise, yep. How do I know the axis is in the middle? So you just have to imagine, like, you know, if you have an axis in the middle and you apply a force to it, which way does it rotate around that center point? You know what I mean? So wherever the axis is, you have to imagine the thing only being free to rotate around that point. Like if the axis is at the center, you imagine this. If the axis is at the corner, you imagine this. If you...
Is it because it's going in this direction?
Right. If it's going the other direction, it would be the opposite. Yeah, if you held this and tapped on the top corner with a hammer, it would make it rotate like this. Yes? The what? Because this length is a meter, and the length of that green line is half of a meter. Any other questions about that one?
So for every problem that we're going to do, we won't have to deal with forces acting on that.
Right. Yep.
I still have a question about the 0.5 meters. So
Yeah.
why is it 0.5 instead of 1? Because if you're looking at the top, like horizontally, like half the distance would be a meter. Why is it the green line instead of
This line?
Yeah.
Because the distance that matters is along the thing that's perpendicular to the force. So a line like this, you know, isn't perpendicular to the force, but this one is. So that's what matters. And yeah. Any other questions about that one? One more? A lot more? Several more? Okay. Okay, so let's say this is, let's say that's 1 meter. And that's 0.1 meters. And here, let's say we apply a force of 200 newtons. And here there's some force F applied. What's F required so that board is, you know, stays at rest? In other words, so the angular acceleration is equal to 0. Well, we have a length here. Let's say the length here is 0.01 meters, 1 centimeter thick. And let's say the mass of the board is 2 kilograms. And let's think of this as like a side view. So there is going to be weight for this board. Okay. A free body diagram. There's a 200 Newton force. There's a downward force at the middle of 2 times 9.81. There's the two forces here that aren't going to affect anything. And then there's a downward force F that we're trying to calculate. And let's wait to, you can do it in any order, but let's wait to calculate the moment of inertia. And, you'll see why when we get to the equation. So the moment produced by the 200 Newton force. The axis is over here. So imagine moving the 200 Newton force down to the middle. Then you have 200 newtons times what's the perpendicular distance to the axis? 1. And would that 200 Newton force make it rotate clockwise or counterclockwise? Counter, yep. And then we have the weight force. How far is it from where the weight's applied to A? Well, that's a little tricky, I guess. The weight acts in the center of that board. So you have to do a little geometry to make this work. The whole board is 1.1 meters long. So the weight is going to act 0.55 meters from the end, right? But this is 0.1 meters. So it's 0.45 meters from here to here. I won't make you do that okay, but it is 0.45. So we have 19.62 times 0.45. Would that weight force make it rotate clockwise or counterclockwise? Counterclockwise. Remember where the axis is. So it would rotate around again here. So if you tap it down, it would rotate this way. Can someone calculate that? Yes. Because, so first I moved the line of action. Got it? Okay. And then the last thing we have is that force F. Again, we have to move that down along its line of action until here. And then what's the distance from this point to the axis? 0.1, yep. And would that force make it rotate clockwise or counterclockwise? That way it would be clockwise, so this is negative. Yes? The 0.001 is just the thickness. And the distance we're talking about now is the distance from here to here, and that's 0.1. Okay, so now let's go to the angular Newton's second law equation. I still haven't calculated the moment of inertia, but we're going to see that it doesn't matter. So let's add these up. We have 200 plus 8.829 minus 0.1 F is equal to the moment of inertia times 0, because we're trying to find this F for when the angular acceleration is 0. This all goes away. And you get that 208.829 is equal to 0.1 F. And so F is equal to 2,088.29 newtons. Yeah, that's the idea of, that's the idea of leverage. That's a lever. The idea is if you are trying to lift something really heavy, you make that close to the axis. And then in this case, since this is so much closer to the axis than the force you're applying, by only applying 200 newtons of force, you can hold up something a little more than 10 times as heavy. Yeah. So why don't I give you one to work on together? So let's say this is a top view. And let's say the axis is here. And let's say there's a force applied of 100 newtons. This length is 0.2 meters. This length is 0.4 meters. And the mass is 10 kilograms. What's the angular acceleration? All right, so free body diagram. There's the axis, and there's two forces there we don't care about. And then there's a force here of 200 newtons. If you draw a line from the axis to that force, you can see it's not perpendicular to the force. What? Oh. I was going to do a problem that was twice as hard. Okay, so that doesn't work, but we can move this force along its line of action, which is this. I don't know if this helps. You can think of it this way. So you can move this force along here, and imagine that this blue line just keeps moving with the tip of this vector as you move it around. So it's like, and right here, that force is perpendicular to the line between them. Yes. No. If you can do it in your head, that's perfectly fine with me. So we'll take this force and move it down to here. And now the line between the axis and the force is perpendicular to the force. The moment produced by that 100 Newton force is 100 times the length of that blue line, which is 0.4. And if this is the axis, would this force make it rotate clockwise or counterclockwise? Counter, yep. So this is equal to positive 40. And the moment of inertia is, in this case, the axis is at the corner. So the formula is 1/3 times, what did I say the mass was? 10. 1/3 times 10 times 0.4 squared plus 0.2 squared. This is 0.16 plus 0.04. Wow, I got to remember that. That works out nice. 0.22, 2/3. And now we can put this into the angular Newton's second law. And we get positive 40 is equal to 2/3 alpha. So alpha is equal to 160 radians per second squared. So the angular acceleration is going to be this way, counterclockwise. Yes? It's positive, so it's going to rotate counterclockwise. Yep. Yes, there'll be a picture. Yep. Any other questions about this one? Okay, well, next week, I'm going to do almost all the same office hours. The one difference is on Wednesday, I'm going to do it from, I think I said 3 to 4. I usually do it from 5 to 6, but I won't have a night class anymore, so I'll do it from 3 to 4. Yes? Yeah, so Monday from 4 to 6, Tuesday from 11 to 12, Wednesday from 3 to 4, Thursday from 11 to 12. Okay. All right, thanks for taking my class. I was going to totally say it patiently and everything. I'll assign the ones that are important. I probably won't. I'll probably do some of the easy ones and not any of the real hard ones, since we haven't spent too much time or anything on this.